with Office Electronics with a brand new project, an updated project actually, because this project, what you are seeing here on this paper, was made with a broken meter before, and now I have a brand new meter here. This meter range is from 0 to 1 milliamp. You can see it here on the box. It says 1 milliamp, original box. And I have two of them, 1 milliamp, two of them, 10 milliamps and 100 milliamps, two of them, and only one amp and one 10 amp. And that's it. This is all the box with these meters that I recently buy. This circuit, I copy it from internet, of course, and it was a little bit wrong, and I modify it. But the biggest problem that I had was this meter. Before it was a VU meter. This is a milliamp meter, so they are different in the markings, but pretty much they are doing the same thing, and they are kind of interchangeable. But the broken meter, the VU meter that I had before, worked for a period of time. After 1 or 2 days, it come back to original error that was having. It was the spring inside that was doing some funny business. The spring that is driving the needle. And I come to the conclusion to buy brand new ones, not scrapped like that VU meter that I had. It was a very good VU meter to a point until it didn't work correctly. And I will probably repair it in the future, but it's very, very fine repairment. It's like a watch, like you are repairing a watch pretty much. And yeah, I'm good, but I'm not that good. So that's it about the meters. This circuit is working for both of them, for both of these meters, exactly the same range. I have what I had before is on this brand new. I changed very little bit from previous circuit to the new one. The only difference, the only change that I'm having from this circuit and this circuit, what you are seeing here, is this potentiometer here, this one with blue, instead of these two resistors. These two resistors are making a voltage divider, and the middle point here is this one single pin here of the potentiometer that is going on that capacitor, at the end of that capacitor here. So this pin of the potentiometer is going to the positive rail, and the other pin is going to the negative rail pretty much. And that's what I'm having here, to the negative and to the positive here, the two pins. And that's the only modification different from the circuit what you're seeing there. In the original circuit, I had 680 picofarads there, but I changed it to 1 nanofarads because I have a ton of them. That 680 picofarads was a little bit not that easy to find. This R2 is 3.6 kilo, and is this resistor here. Unfortunately, I remained with this value from the original circuit because is influencing a lot the needle, the meter. When I try to put a better value here, easy value to find, to make a more nicer circuit with a better value there, it's changed all the dynamics, all the travel of the needle, and I had more problems than I asked for. So it remained for both meters before, and this one, the brand new, what I'm having here. Originally, the circuit was powered from a battery, and I have here some notes. This circuit is very voltage dependent. The scale of the meter changes if voltage is not 8 volts, exactly 8 volts, what is marked there. Also, I'm marking the 8 volts from a power supply, and I can show it to you actually. There it is. That's the voltage on top, and that's the amperage. Right now the circuit is using 10 milliamps. So this 8 volts value that I choose it. The original circuit, I think it was using a 9 volts battery, and usually those 9 volts are a little bit over 9 volts. It's 9.2, 9.3, probably 9 when the full battery is brand new. But I choose this relatively random value. This 8 volts is a very random value to be as close as possible to the original voltage, to that 9 volts, but not too low, not too high. It's not something that you must stick with it. If you are designing this circuit and you want another voltage value, you can do it so. But be aware of the 555 is working from 4.5, so 5 volts pretty much, to the maximum 16 volts. Probably 15 is more safe to be maximum. Pretty much this entire circuit can go up to 15 volts because of the chip there. Otherwise, other components doesn't care that much. This is not a standard value. It's just a random value that I choose to. It's very voltage dependent, this entire circuit. So I have to insist, if you change it to 7 volts or to 9 volts, the travel of the needle is changing drastically. It's getting out of the calibration pretty much. Right now it is calibrated as I wanted it to be. This QX, it means the capacitor in test, which is this one. And I calibrated the circuit with 100 ohms for the maximum travel of the needle, and with 1 ohm or 500 milliohms for the minimum travel of the needle. And I have to redraw the scale. The scale, it means this, what you are seeing here with white, to fit the minimum, maximum, and other resistors values. Because right now what you are seeing is milliamps there, but I have to make a new scale, a new label, and to stick it on top of this one with a piece of paper, most probably, and to redraw the scale to represent the resistive values of the component in test here. Either is the capacitor or the testing resistors that I'm calibrating everything right now. So that's what this note is, its meaning is. Okay, I had here in the original circuit from the internet a Schottky diode, but was shunting the output, and I took it out from the circuit completely because the travel was in a side of the screen, and it was doing more harm than good. So I reshaped the circuit a little bit. to fit my meter, what I'm having here. And I think this circuit, what you are seeing here, is a bit more better than the original that guy made it. R1 for calibration, needle position on maximum 100 ohms and on minimum 1 ohm. It means this resistor here, this potentiometer, what you are seeing here, is added very late in the progress of the circuit and calibration. But until this potentiometer, I actually used these two resistors on different values, and a little bit too late it came to my mind to change these two resistors with a single potentiometer, and is doing a phenomenal job, is doing the correct job. I didn't trust originally. I thought maybe it will do a funky job, but I said I will try it anyway, how bad it can be. And to my surprise, it did a perfect job. It is linked here, the two legs are linked to negative rail and to positive rail, as you can see here. This is the negative rail here, this end of the potentiometer, and this is the positive rail with a switch there, and in the middle, which is this pin of the potentiometer, is to this link to that capacitor, which is that, and the diode, this SMD diode. That's this node. This R2, like I said, is a protection maybe for calibration, is mostly for protection for the meter itself. But if you change it, like I said already, if you change it, it will fuck up the entire reading and calibration of the meter. I got stuck with it. Also, this capacitor here, C1 value, sets the maximum needle position. If you change it to a lower or higher value, from this 100 nanofarads, this one here, it will change the position of the needle to the more to the maximum or to the minimum. As it is right now, is calibrated with this 100 nanofarads. So these are all the notes what I'm having here on my paper. Another very interesting detail. Let me take the brand new one. When I received this meter, is the exact same meter, is 1 milliamp like this one. This is the package that it came with. God damn it. This is actually set to 0 there. But this one, when I open it, originally the needle was not on 0, it was on 0.2 all the time. And it took a while to figure it out, to understand what is going on. While I didn't pay attention originally to this little detail, where the needle is set originally. So if I'm taking this one out from here, you see where is the needle now? Is way outside the scale. And if I'm putting a maximum signal, it will go to the other outside of the scale also, here somewhere, outside of that one. When I receive it, the needle was not outside there, like it is right now. It was on 0.2. And I had to take out this little screw here and this other one, and take out this case. And if you can see there, I hope you can see inside where this screw, plastic screw is not a screw, is off-center pin that is theoretically is moving. That is like two parallel bands, metal sheet of band, and I had to move with my finger that thing left and right here, and here probably you can see it. Let me show you mine. You see how way in this side I push it that way to actually get the needle position on the minimum here. So I had to modify a little bit how it came. When it came from new, it was a little bit fucked up, and I didn't know. I don't work with, usually I don't work with this type of components. So this is a little detail that you have to be aware of when you're buying this kind of meters. Right. Next, the calibration itself. The calibration of this QX, of this capacitor, which I used resistor values pretty much. And I have here, these three guys are 1 ohm each. And I will show you, I hope it will show good enough. Let me actually show you a better calibration that I did. I'll use a link, a wire link. It's a simple, this is not a resistor, this is not a component, this is a pure wire. It's a simple wire. And this was one of the first calibration, what I did, and it helped me a lot with this. So what I'm doing, I'm linking, I'm shorting pretty much from this point to this point. Imagine this capacitor is not here, and it's only a wire from that point to that other point, to the negative rail. From this point, which is because of those capacitors, of this entire circuit that is oscillating, this oscillation point, and to the ground, pretty much. So this was the first calibration. And as you can see, it's going to 0.2 there, fixed on the money. I hope you can see it. Yeah, like that. Yeah? Right on the money. And when I'm taking it out, so this is the minimum. This link represents the 0 ohms, pretty much. But this wire is also having a tiny little bit of resistance, and most probably is 1 ohm or a couple of hundred of milliohms, probably. I'm not sure. You'll see why in a second when I will test the actual resistors. You'll see. The needle will go even less than 0. This wire link calibration here, it will go a little bit less. So this link might have a tiny little bit of resistance on it. And here is going from 0.2 to 0.8. And this is all the traveling. So this is the maximum when it's without anything there. When this capacitor is not connected pretty much, this is the maximum 1 mega ohm, let's say, the maximum resistance there. And it's going right on the money on 0.8. So this is the calibration I had to play around. And I worked with this potentiometer to actually center it like this, using the link and taking out the link and looking where it's landing the needle on maximum. And I was lucky to have this range exactly on the scale markers or lines there. I was very lucky. It could have been a little bit less there or more. I couldn't figure out the values of the components in this circuit to modify them to obtain from 0 to 1 there. I wished I could make it a little bit larger travel, bigger range of the travel. I wish I could, but I don't really know how to do it. This width is like a constant and is shifting either too much to the left or too much to the right, but it's pretty much kind of the same width. I don't know why is that. Probably the frequency from this oscillator here. This is an oscillator including the 555 with this two capacitor there. Probably the oscillation is making this travel. I'm not completely sure exactly how to modify it. If someone else can figure it out, is better electronist than I am, do announce me. I want that modification myself to know about it. But for now, this is the travel from 02 to 08, and it's good enough. Now, let's test 1 ohm, and I will insert it here. And it will go right on the money on 0.2 as well. I hope you can see it good enough from this angle. If you're watching it from my perspective here, yeah, you see it's like this, probably, right on the marker. I was able to drive the needle exactly on that marker from this potentiometer. So this is 1 ohm. Now I will insert another 1 ohm in parallel. It will mean 0.5 ohms or 500 milliohms, like you are seeing it here mentioned, 500 milliohms in parallel. Huh? And you will see a tiny little bit of deflection. I'm not moving the entire system here. You see? It deflected a little bit more to the left, the needle. So pay attention to the needle. If I'm taking it out and moving it here, it's not my movement because I'm moving the entire system. The needle is actually moving a little bit less towards the 0. So now it got a little bit to the right. Yeah, you see? And now a little bit to the left. And now I have a third one. So 1 ohms in parallel. It means 333 milliohms. But unfortunately, it's not a big difference. You can barely see a little bit of the needle moving back. But it's so fragile. Yeah? Can you see it? It's like it's so small of a difference. It's very, very small. I can see it a little bit, but it's too small. So it's insignificant. So now when I'm taking out this from 500 to 1 ohm, you will see the difference. Back, you see? It moved a little bit to the right. And it's very interesting that it can measure this very tiny resistances. I wished I was having a little bit more travel to from 1 ohm to 500 milliohms to 100 milliohms to see that small resistance even better. I think in all my experiments, I managed to make the needle move that way a little bit, but a little bit more better than it is right now. But I don't know what I did, so I settled to this arrangement, what I'm having, with this result, what I'm having right now. But it would have been better if I was having a better range for milliohms, under 1 ohm. It was nice. This next resistor is 10 ohms. I know you cannot read it from the markings there because those are retarded markings. But trust me on my word, this is 10 ohms. And 10 ohms is jumping to close to 0.4 a little bit. Not exactly on 0.4, is a bit to the left. So this is 10. And also I have 100 ohms. This is the maximum for the calibration that I used here and also here. For this, I calibrated 100 ohms for the maximum and with 1 ohm for the minimum of the travel of the needle. So this is 100 ohm. And the needle is going a little bit back, not much. You see, from 0.8 exactly, a little bit like 2 lines. Probably to 0.7-ish. Kind of 0.7. And now I can put another 100 ohms in parallel, so it will be 50 ohms. And the needle got even back towards the 0.6. And another one, and it will be 33 ohms. And it's going right on the 0.6. On the 0.6 is 33 ohms, pretty much, there, what I'm having here. 33.333 ohms, what I'm having here. Of course, these are 5% tolerance. They are not super precise. If I'm actually using 1%, yeah, the same, with 1%. So if it's 5% or 1%, it's doing the same business. It's moving a little bit there. But it's better to use this 1% tolerance resistors than the 5% tolerance resistor, especially for calibration. And that's it. This is all the calibration I did with this meter. I really like the range from 02 to 08. I wished I was having from actual 0 to actual 1. The next step to make a label, a new label, and to glue it there on top of this one that is right now, and to actually show how many ohms, the resistive values. And right now we can actually use a capacitor here and to read it. I have here a bunch of components, and I have this guy. What are you? 400 microfarads, 25 volts. Right? This is negative. It's polarized, so we have to be careful. And it's going right on the 1 ohm range, like it's nothing, like it's a single wire there. So this capacitor is very good. And let's try this other one. This is 1 microfarad, 50 volts, also polarized. Opa, This is not that good. This is not that good. It's a little bit funky. So yeah, I have a bad one. I didn't know, but I'm still using it because it's for testing. This is 1 microfarad at 50 volts, and probably there is a list of voltages that everything can fit. It's a range of values. Probably this guy is fucked up. So I had a good one and a bad one to prove it that this circuit and this meter is showing a very interesting reading of the capacitors or equivalent series resistor for the capacitors in test. That's it. This is it. This is all the testing. And next, after this test circuit that I made here, I will actually build all this circuit on a single board with some pads, specific pads to use the components in test. This circuit is good both for capacitor but also for very small resistors. You can test them, and also, why not, some weird wires, probably like a nichrome wire. If I want a special resistive value, I can use it to actually give me a reading on it. The final version will have some special pads. I was actually thinking on adding a digital meter here. It crossed my mind when the first meter that I had was broken, and while I was repairing it, I was trying to repair it, and I succeeded for a little bit, but then it fucked up itself. It shit itself for some other reason. I cannot explain why. While I was repairing it, I was thinking on adding a digital reading, and it's so fucking complicated. It's a bit more complicated than I anticipated. It's a lot of components. It will complicate this very simplistic, very basic circuit. What you are seeing here is very basic, very easy to do. I like the simplicity of this circuit, and this meter that you are seeing here is this component is a simple meter. It's not complicated. It's very simple, very easy to use. That's why I put the money. So this single component is adding a lot of simplicity to the circuit. It's part of how simple everything is, and that's why I invested a little bit in a couple of them. They are easy to use, easy to understand, very straightforward, and you have to pay attention and to take care not to blow them up. But pretty much that's it, you know. Unfortunately, they don't have a protection circuit. You have to be careful and to create a protection circuit for it. Other than that, probably from just a simple resistor and one single resistor probably is the only protection it needs, most probably. But it's very simple component to use, and I love it. I love simplicity. I love simple circuits, not unnecessarily complicated. A digital multimeter will unnecessarily complicate everything, and it will add another complicated layer of circuitry that fucking hell. And I didn't want that. In a sense, I wanted to remain on the same philosophy and the same mentality of the original circuit, because this is an old circuit from the old magazines. And that guy saw it and applied it. He created his circuit, and he probably copied from an old magazine, most probably. And I wanted to remain on the same track, on the same philosophy, on the same the analog mentality. Yeah. So the next step is to actually make the board, and also a case that is enclosing and is securing everything and is covering and protecting everything. That's the next step. Until next step, I say goodbye and see you later. That's it for now. I hope you like it. Please leave a like. See you later from your favorite artist electronist, Mr. Q12. Bye bye. Bye bye.